Having seen the breadth-first traversal in our previous video, it's time to explore another powerful graph traversal technique, and that's called the depth-first traversal. It's also known as the depth-first search or DFS. Depth-first traversal prioritizes depth over breadth. So you use DFS if you want to go as deep as possible, as fast as possible. Let's dive right in. On the left side, you see a simple undirected graph. On the right, you see its adjacency list. As opposed to the breadth-first traversal, we need a stack to perform the depth-first traversal on a graph. Luckily for us, this stack is automatically managed as long as we use recursion. This is one of the reasons our DFS algorithm will be recursive. We start from vertex A, immediately marking it visited. Then we choose any adjacent vertex of A and recursively perform a depth-first traversal on that node. Let's say we pick C here. Mark the edge AC as discovery, mark node C as visited, and descend down into one of the adjacent vertices of C. A is already visited, so we don't go that way. We have 4 unexplored options: B, D, E, and F. Let's pick, say, vertex E. Mark it visited and mark the edge CE as discovery. From here, we have 2 options, B and G. We pick G, and then we go to H and then D, and we mark edges EG, GH, and HD as discovery edges. Now here, we see that D has 3 adjacent vertices. A and C are already marked as visited, so we can go that way. In fact, we'll mark these edges as back edges. Back edge in a depth-first search is identical to a cross edge in a breadth-first search. It's just a different term. So AD and CD are marked as back edges. Here at vertex D, the only way forward is the adjacent node F. We go to F, mark F as visited, also mark the edge DF as discovery. At vertex F, we have 3 options, D, C, and G. We can't go to any of these because all of these are already marked as visited. Now, edge DF is already labeled as discovery edge. We mark the unexplored edges CF and FG as back edges. We have explored all the vertices adjacent to F, and there is nowhere to explore. We have checked all the surrounding vertices, so we backtrack to its parent, which is D. Here at D, we had already explored all of its adjacent vertices and there is nothing new to explore. So we backtrack to H and then to G. Last time we crossed G, we picked H and skipped F for later. Now we are back at G again. It's time to explore F that we had missed earlier, but unfortunately F is already marked as visited. And also the edge GF is marked as a back edge. There is nothing more to explore at G, so we backtrack to E. Here at E, we previously skipped B and chose G, but now it's time to go to B. We mark the edge BE as discovery and mark B as visited. At B, we notice that all of the adjacent vertices are already visited, but the edges were unexplored. So we mark the edges AB and BC as back edges. Nowhere else to go from here, so we backtrack to E, then to C, and finally to A. Here there is nothing new to explore. All of the adjacent vertices of A have already been explored. We simply exit from the DFS. The discovery edges here represent one possible spanning tree. Recall that the spanning tree is a subset of a graph which covers all vertices. It's a tree structure with no cycles. The way you select the adjacent vertices at every vertex in a depth-first traversal can result in a completely different underlying structure. So let's go and let's do another quick example on the same graph.